I was going to say that 7 years ago, today was exactly my second week working for Alex as a postdoc. I was very excited, and for the following years, I learned a lot from Alex, a lot of science, writing, the way of thinking, and a little bit of squash playing as well. We started out developing a time-dependent density functional theory approach for calculating dispersion interactions. And then later, when I moved to Montana, we started to do spectroscopy calculations using TDDFT on the larger molecules. And when I was a graduate student, my mentor was also Shi Chu here. He's also a graduate student of Alex. And I learned to use TDDFT to do strong field calculations. And then inspired by all this work with Alex, we further developed a new approach that is a multi-configuration kind of approach to calculate strong field processes. Okay.
The little microphone has got dislodged. Perhaps you could speak in to here. It's just your microphone is at the side, and it's very difficult to clip it in correctly.
Okay.
Yeah. So perhaps this might be then the people like Vasily can hear you. Give the.
I'm just looking on leaves. It's okay.
Very good. Okay, thank you.
I don't have to restart, do I? Okay, good. Okay, when explicitly expressed as time-dependent functions, TDDFT formalism bears very much resemblance to TD-Hartree-Fock equations. The difference lies in the potential. There are quite a few ways to formulate the density functional kind of potential, and this is what we use. Is there a better pointer? This one. You see the pointer? Oh yeah, good. Okay. So this is what we use. OEP here stands for optimized effective potential. SIC is self-interaction correction. Sigma here is the spin index. R is the electron coordinate, T is time. And then this is the external electric field. This is electron nuclei Coulomb attraction. This is electron-electron repulsion. Rho here is electron density. This is a very important term, exchange and correlation functional, expressed as functionals of spin densities. We also have an explicit self-interaction correction term added here. This way, we make sure that the long-range part of the potential will reproduce the correct asymptotic behavior. Therefore, the excited states and continuum are much better represented, which are a requirement for accurately calculating polarizabilities. The accuracy of a density functional-based approach pretty much lies in the choice of exchange and correlation. If we replace the time set the time to be 0, if t equals to 0, then this reduced to the static potential as in the Kwangshan equation. This is the Hamiltonian for a Kwangshan equation. So if we solve the Kwangshan equation, we obtain a whole set of spin orbitals and the associated energies. And we use these orbitals and energies to construct a linear response function. The linear response function is defined by this equation. R and R prime, again, are electron coordinates. N here is the occupation number. And the phi's and epsilons are from this equation, and omega is the photon frequency. So if we have this frequency-dependent response function, and then if we obtain also a frequency-dependent field, we multiply them, do an integral, and then we get the induced dipole moment divided by the field strength, suppose we will get the polarizability, except that it would take some effort to figure out that frequency-dependent field. It's not just the external field, because if we take another look at the time-dependent potential here again, in addition to this term, there are several other terms are time-dependent. The time dependence of these terms is because of the charge is oscillating and moving in the field. And that will also create the electric field. And that in combination with the external field is what we're trying to compute, and it's called the delta V self-consistent field here. So this is defined as a Fourier transform of this time-dependent potential, and it's supposed to match up this time-dependent formalism term by term. Except here we incorporate the self-interaction term into the exchange and correlation. I want to draw your attention to the last term here that includes a functional derivative. This is called exchange and correlation kernel. The accuracy and correctness of TDDFT kind of method pretty much depends on the correctness of this term, the kernel term. Then we solve this equation and this equation self-consistently, as we see that the delta V depends on delta rho, and delta rho depends on delta V. And then once we reach the self-consistency, we plug this delta rho into this equation and to obtain the polarizabilities we needed. As explained by several previous speakers, and we need polarizabilities at imaginary frequencies to calculate dispersion coefficients. Then we calculate the isotropic polarizabilities and isotropic C6 dispersion coefficients for many species across the periodic table. The C6 coefficients is for like atom pairs. We did the calculation for the main group atoms up to the 5th row, and the 1st row transition metal elements, and Y, and L8, this entire row of rare earth atoms. It was a very fast process to obtain isotropic polarizabilities and dispersion coefficients in terms of computation. But it's a relatively slow process to validate them by comparing to what's out there in the literature. I'm very amazed that Alex could just determine a most likely value for almost all these atoms. And then we can compare our calculation to those most likely values. We are happy to see that the disagreement is within 9% for polarizabilities, and within about 8 or 9% for dispersion coefficients. I hope you don't use the standard of our first speaker to evaluate our results. It's different. Then if for these atoms, if the angular momentum is larger than 0, the polarizability is actually anisotropic. So we have to determine a rank 0, this is isotropic polarizability, and also a alpha 2, which is an anisotropic polarizability. The way we're doing it is that for each M state that can be represented by a single determinant, we calculate a couple polarizabilities, namely the parallel and perpendicular polarizabilities. This m quantum number is defined as the projection of angular momentum to z-axis. And then the parallel and perpendicular polarizabilities are related to the alpha 0 and alpha 2s by these two equations. So this way we can calculate alpha 0 and alpha 2s for many open shell atoms. The largest largest angular momentum we calculated, I think, is L equals to 6. That is in the I state. And then once we have those alpha 0s and alpha 2s, we can use this equation to calculate the C6 coefficient for an open shell atom plus a helium atom. The polarizabilities for helium atoms are isotropic. And then this is also, C6 can also be further expressed as a function of C60, which is isotropic, and C62, which is anisotropic. They can be obtained from alpha 0 and alpha 2s of the open shell atoms. Then we did the calculation of C60 and C62 for scandium and titanium, and compared to what's published in literature in this paper. And in this paper, for dispersion interactions, they use a pretty large supramolecular calculation of CCSDT, I think, with very large basis sets. We see that the spherical dispersion coefficient, the isotropic dispersion coefficient, the agreements are pretty well, particularly for scandium. And then there are some difference in the C62. It's hard to judge. Using their method, it's very hard to obtain the C62 for open shell atoms, particularly because of basis set superposition error. Then these are the values we obtained for rare earth atoms plus Y. They have some, if we look at the configuration, they have a lot of similarities. These have xenon core, and then you have completely filled 6s or Fs shell, and then partial filled or completely filled F shell, and occasionally you have one D electrons. And these are the terms. So the state ranges from S to I. If we just look at the trend of these 4 columns of data, the absolute value all in general decreases with increasing nuclear charges, with some exception. The exceptions are when there's this a D electron in the configuration. And then we'll also find that the C62 is very small in magnitude compared to C60. The reason why polarizabilities decreases with increasing charge, nuclear charge, is that then electron density is pulled closer to the nuclei, and therefore they're not as polarizable. We don't have any, we haven't found any experimental data to compare with for alpha 0. However, alpha 2 has been measured by measuring the Stark shifts. So that's something we can compare with. So these for duplet D states atoms. If we look at the alpha 2 values of these 3 elements, that's the calculated value and this is the experimental value. I was happy to see that the agreement is amazingly well. But then there's this LU that the disagreement is amazingly large. We see that from the theoretical prediction, it follows a trend that the polarizabilities decreases with the increasing nuclear charge. What's different in these three atoms is just that here the F shell is empty, here is half filled, here is entirely filled. So the way to rationalize this really large experimental value is probably because once this F shell is completely filled, it becomes particularly pulled towards the nuclear core. We don't know whether or not that's the case, but that's the way to rationalize. When it's particularly pulled towards the cores, it probably that will shield the d electron from the nuclear charge, and the d electron is responsible for the anisotropy of the polarizability. So if that's the effect, and this is the effect that's not reproduced by our theoretical calculation. And then for these for those H state atoms, and the agreement between the experiment and our calculations are very good again.
There you go.
So for these atoms, the agreement between our calculation and experimental values are very good again. For these I states, we have the sign correct. I think it's probably because the angular momentum is just too large, and plus the spin term multiplicity is very large as well, and this is a very small value comparing to the alpha zeros, so we overestimated obviously the alpha 2s here. And then for a slightly lower angular momentum, we get very good agreement again. So now there's something different. Using TDDFT formalism, we can also derive a Hamiltonian that very much resembles CI single. And then by diagonalizing that Hamiltonian, we can calculate excitation energies and transition dipole moment to excited states, and to compare with experimental spectroscopy. Here we studied the spectroscopy of terpyridine, ruthenium-2, and platinum-2 complexes. This complex, terpyridine, are the three rings with 3 6-member rings, and each with nitrogen in it. And here too, that's the terpyridine. And then the metal in the middle is different. This one is for ruthenium, and this one is platinum. This complex has been studied for about a decade, and this one is newly synthesized by our collaborators. The reason why we are interested in these complexes is that the terpyridine can attach to biomolecules through intermolecular interactions. There's a lot of pi-pi stacking interaction going on. So we're hoping to attach them to biomolecules in vivo. Then they can serve as probes for pump and probe experiments to study the dynamics of biomolecules in vivo. So that's the ultimate goal. And the first step is to study the spectroscopy, to fully understand the spectroscopy of them and understand how intermolecular interactions influences the spectroscopy. The amount of data we obtained for these two complexes is huge. So okay, I tried that before, it didn't work. I just pick a couple out of the large amount of data we calculated for these complexes to present. One is for the monomer singular state of this complex for calculating the absorption spectrum. And the other one is for the luminescence spectrum of this complex, dimer and triplet transitions. In this table, we have listed the excitation energy of our prediction and their translation into wavelengths and experimental data, and also calculate the transition dipole moment. The experimental data gives a band. That's because of the vibration. And without evaluating the Frank Condon factor, we're hoping that the excitation energy calculated can fall into the range of these bands. That's the case for the second transition, and not exactly true for this one. The calculation also gives the major contribution of orbital transitions. And for this one, it's mostly 88% HOMO to LUMO transitions. The HOMO looks like this, and the LUMO looks like this. And here, this is where the metal is, and then this is where the ligand is. So here is what we call a metal to ligand charge transfer. For this kind of transition, in order for TDDFT to obtain a very accurate excitation energy, you have to have a very accurate long-range potential again, which we don't have here. We didn't do the self-interaction correction. Instead, we use B3LYP. So if we simply take the orbital energy differences between HOMO and LUMO, and that will correspond to a wavelength of 389 right in here. And the second transition corresponds to HOMO -4 to LUMO, and HOMO -1 to LUMO +4 transition. The spectroscopist was able to assign this kind of peak without really doing calculation. And our calculation kind of confirmed their assignment with slight corrections. And then for this newly synthesized complex, there are all these spectroscopy data. Particularly this one, there's one that is a concentration-dependent 603 nanometer radiation that is very hard to assign. And the thing is that they don't even know whether this complex can form an oligomer in a solution. And then we provide the calculation showing that yes, they can. And then we also are able to assign that it's probably most likely due to a transition of triplet state between this HOMO and LUMO orbitals. And then the orbital energy difference will correspond to a 332 nanometer, pretty close to this range. And I'll just jump to the conclusion. So in summary, we have developed a linear response TDDFT function, a theory approach to calculate dynamic polarizabilities and dispersion coefficients. And for most cases, the accuracies as such, the error for dynamic polarizability is about 1% to 8%, and for C6 coefficient is between 1% and 9%. And we can also use TDDFT to calculate excited state properties and compared to electronic spectroscopy. There's also this newly developed approach for strong field processes.
Wonderful, Steve. Thank you very much for that. Gosh, those big biomolecules, they're something else.
Yes.
To do such lovely work on those truly is very, very nice.
Thanks.
We'll open the paper for discussion. We have time for a few general points. We survive the computer. You can repeat yourself again, please.
What do you use for your exchange correlation functional?
For which calculation?
For the atom ones, the ones where you calculated the coefficients, the C6 coefficients for the periodic table.
Okay. That we use just the local spin density approximation as a foundation, and then we added the self-interaction correction to it. And the way to add it is go through this optimized effective potential kind of formalism to obtain this self-interaction correction term and add it to it.
Thank you.
Thank you. Any further discussion, etc.? Well, thank you, C, for surviving this computer. Whatever happened, we were able to keep the slides going. Thank you.